Alright, so welcome back, and in this lecture we'll be talking about Chapter 20, introducing this topic of modulation here. So here are your objectives. We're going to be talking about this concept of a baseband and some potential limitations associated with transmitting it, discussing the role of modulation and how that increases our capability to transmit, as well as other methods of modulating. We're talking about looking at plots of AM signals and determining values from that, and then we're going to be creating frequency plots to determine sidebands and bandwidth of AM signals. We'll also discuss the concept of overmodulation, and that'll be embedded inside the lecture. So moving forward. So a baseband signal is simply an information signal at its original frequency. And one of the key concepts here is this is typically at a lower frequency. And when we're transmitting a baseband frequency, so physics is going to dictate that the antenna length is tied to the signal's wavelength. We're actually going to do some practice problems here to look at that. So we see here that we have a tuning fork. And that tuning fork creates a 440 hertz signal. So if we were trying to transmit that on an antenna, we're going to try and see how big that antenna would have to be if it only has to be 1/10 of the size. So key here are 440 hertz, and our antenna is 1/10 the wavelength, lambda. So what I want you to do is go ahead and pause the video, come back, and we will work through that problem. So now that you're back, let's go ahead and remember our equation from chapter 19, where lambda is going to equal C over F. Remember, that comes from the equation C equals wavelength times frequency. So in this situation, we're going to go ahead and say lambda equals 3 times 10 to the 8th meters per second, all over 440 hertz. And remember, hertz can be gotten rid of, and we can just replace it with 1 over seconds. Cancel those out, and this is going to end up coming out, if you pull out that calculator, to 681.8 kilometers. So if this is our wavelength, and we have to have an antenna that is 1/10 that size, we end up finding out that our antenna has to be 68.1 kilometers long. This is completely unreasonable, and leads us to say we have to do something about that, and that's where our modulation stuff comes into play. So let's move over and look at another question. And this question, it says, hey, we have the wavelength of an AM radio station, and AM is going to be primarily the topic of discussion for this entire chapter, and it's at 1,430 kilohertz. So if we take 1,400 kilohertz, I want you to pause the video and work through that same type of problem to try and figure out what is the wavelength, and then for part B, go ahead and figure out what the antenna length would have to be for that situation. So using all the criteria here, whereas the antenna will be half the wavelength instead of 1/10 the wavelength. So pause it, work through those, come back, and we will work it together. Okay, now that you're back, let's say recall again. Lambda equals C, the speed of light, over F, the frequency, and do that out. That's 3 times 10 to the 8th meters per second, all over 1,430 kilohertz. So we'll just do times 10 to the 3rd, and we'll hertz. Get rid of that. Give us 1 over s. Do some cancellation. Get rid of that. Get rid of this. Make that a 5. And just end up pulling out the calculator anyways. And that's going to give us a wavelength of 209.8 meters. Take that 209 down here to part B, 209.8 meters, and then we know that we need an antenna that's 1/2 times lambda, and do that quick math with your calculator or on your own, and you're going to end up with 104.9 meters. And this is a lot more reasonable when we start thinking about driving up and down the highway, seeing antennas along the roads. That actually seems like something that's feasible. So what I'm going to do now is I'm actually going to stop this video, take a break, or roll right into the next video if you want to. And after that, we will get into the topic of modulation. So as we just saw in practice problem 20.1, it's pretty impractical for us to build antennas for some frequencies. And if you think about the fact that our human voice has frequencies from 300 to 3000 hertz, this turns into antennas that are 100 to 1000 kilometers long, which is pretty unrealistic. So what we do is we talk about this concept of modulation in order to increase our ability to transmit over distance and have reasonably sized antennas. So the concept of modulation is impressing information onto a carrier signal, and I want you to understand that modulation is it's varying a or more properties of the wave, that electromagnetic wave. And if you recall, those properties are amplitude, frequency, and phase. So when we're modulating, we're talking about two different signals here. We have our information signal, which is lower frequency, and our carrier signal, which is higher frequency. And we can see here in these waves, the lower frequency has more spread apart wiggles, whereas the higher frequency bounces back and forth much more rapidly. And if you remember that frequency and wavelength are inversely proportional, if you remember that from your math classes, that means that as one goes up, the other goes down. So with lower frequencies, we have longer wavelengths. And for higher frequencies, we have shorter wavelengths. And because of that, this allows us to say, hey, if we have a carrier signal with a higher frequency, that shorter wavelength then means a smaller antenna. And if you have the time and really want to look into it, standard cell phones can be operating either at 800 megahertz or 1900 megahertz. These are approximate. And you can figure out approximately how big your antenna would have to be based on the previous practice problems we've worked. And they can give you some kind of concept of how that works. But moving forward, in order for us to modulate, and this is a horrible color, so let me get that adjusted for you. To modulate, we need a modulator. And those are going to be a device that allows us to vary the amplitude, frequency, or phase. And let's take a look at some of those waves as they've been modulated. So we see here we have an amplitude modulated signal where we have the information signal come in, has a carrier signal here. This AM modulator then spits out this wave here that has been modulated as far as its amplitude has been varied. In frequency modulation, we have an FM modulator with our carrier signal, and we see that the frequency is modulated after a certain point here where it gets to be a slower frequency or a lower frequency and then a higher frequency, so on and so forth. And this actually appears to be digital modulation or digital frequency modulation for this example. And then we have phase modulation here. Phase modulator, we see that that phase is shifted every once in a while. Here the information wave is actually shown as digital pulses. Again, this looks like another digital example. However, for what we're talking about, we are going to focus on amplitude modulation, primarily because it's going to be the easiest to visualize as well as the most simple to implement. So let's move forward. Just recapping some of that information and showing a little closer example as to how this looks, and capping on the fact that amplitude modulation is varying the amplitude of the carrier wave. Okay, so how do we do this and how do we think about it? And what I want you to think of is and know is that the AM wave, the amplitude modulated wave, is the product of the modulating signal and the carrier signal. So if you look back to the previous slide, you'll see that VC, dependent upon time, our carrier signal has a form of capital V sub C cosine 2 pi f sub c of t. And it can have a phase, but we're going to leave it without a phase. Now, you can recall as well that our message signal, V sub m of t, equals capital V sub m cosine 2 pi f sub m of t. Again, it could have a phase, but we're going to leave it without a phase in this situation. Now, when we talk about the product of this, it's actually going to be slightly different. And one quick note, I know that in the past we used sine waves. Cosine waves are interchangeable here. There's just a phase shift between the two of them, and we can write it this way without any issues. So don't get caught up on that, please. So when we're moving forward and we're talking about this in the time domain, and we say that we want to discuss the product of these two, the modulating signal and the carrier signal, we're going to write this out as V sub AM, that's our amplitude modulated wave, time dependent, is going to be capital V sub C plus lowercase v sub m of t times our cosine 2 pi f sub c of t. And when we are looking at this, I want you to know this. This is the same as that. That is the same as the amplitude for the carrier wave. In all situations when you see that inside of the equations or in other places, that's what that value is equal to. And when we do the math here, we're going to end up with V sub c cosine 2 pi f sub c of t. And this is our original carrier wave, but we add in this product v sub m cosine 2 pi f sub m of t, and this is going to be multiplied by cosine 2 pi f sub c of t. And we're going to talk about how to handle this in the future, but this is what that amplitude modulated wave is going to look like when it's expressed mathematically. You know, for some of you this is probably uncomfortable, but we're going to get into all these things and we're going to break it down a little bit in the future. But this is where it starts, this is how it's going to look, and we're going to go from here. Now let's look at some plots and we can see if that'll make things a little bit more graphically understandable. So we see here in the top we have this information signal. It starts off by having no signal at all. Then it kicks on and it starts kicking this out. The resulting amplitude modulated wave is down here. So we have our carrier signal, nothing happening to it because there's nothing going on before this time. So it's just its normal self doing whatever that carrier signal is going to do. However, as soon as that modulation signal kicks on, we can see that it starts affecting it this way. Then it goes on and through here. So in this situation, what we have is we actually have two signals where the one signal is 7.5 times, or it has an amplitude of 7.5 and a frequency of 440 hertz. So if we pull that out, we have V sub m equals 7.5 and f sub m equals 440. Down here we can see that the Okay, so looking at these two plots, we're going to start by saying, one, we have our information signal plotted here, and we have our amplitude modulated signal plotted there. So we can see, based on this original portion here of our information signal, that up until a little after 2 milliseconds, we have nothing going on. There is no signal present for the information signal. And that translates down to our AM wave just being our original carrier wave, V sub c of t, with no modulation because there is nothing happening in the information signal. However, as soon as we have activity in the information signal, we see this modulation to the amplitude. And this effect is based on multiplying our carrier signal by the value of our information signal. And these two signals we have V sub m given there, but just, you know, V sub c of t equals 10 sine 2 pi 5,000 times t. So we can see that even when these things are together, when they are modulated, they have their individual frequencies and then they have a collective frequency. So we can see that we could measure the frequency of our carrier by measuring peak to peak, determining what the time difference between those two are, and working from there. So in this case, if we blow that up and we look here and we go, hey, this is our t sub c, and let me erase that, get a much finer pen. T sub c there. Then from T sub c we can find f sub c. Or go over here and we look from the peak of the wave there to the peak of the wave there. We see that it also translates like such. And it's still going to be T sub m. And from T sub m, we can find f sub m. So this is going to be a way for you to look at those plots and be able to extract some of that information and see how that product plays out when you're multiplying your information signal by your carrier signal in order to get that modulated wave. So what I'm going to do now is I'm going to stop the video and I'm going to prepare to roll into the next section. Take a break if you need to, otherwise roll right in. Alright, so welcome back. So when we have this amplitude modulated wave, one of the things that I want you to know, and the way we extract the information from the amplitude modulated wave is from what's known as the envelope. And the envelope is just this dotted line. It's the outline of the outermost portion. And if you were to match that up against your original wave, your original information wave, you're going to see that that is going to match up to that. So we need this envelope to be as defined as possible. And on the receiving side, it's going to get extracted, and that's where we're actually going to get our information. But there's an important concept here, and it's a relationship between our amplitude of our message wave and the amplitude of our carrier wave. And it's known as your modulation index. And it is found, and well, it's known as M, and it's found by this equation, capital V sub M over capital V sub C, and it's listed as a percent, so it's always going to get multiplied by 100%. And we're going to look at some examples of different modulation indexes and some potential problems that come with that. So on this slide we see multiple different modulation indices, and when we're looking at these, I want you to pay attention to the axes and see how far apart your maximum and your minimums are inside of your different modulation schemes. So for example, on this one, it ranges from 15 down to 5. So that's only a 10 unit spread between those maximum and minimum. And if there's noise in the environment, that may affect things and may make it hard for us to understand what's going on. Whereas with 100% modulation in this situation, we range from 20 all the way down to 0, which gives us a lot of range, and if there's noise in the environment, it can be it's easier to extract that information appropriately. One of the things that you're going to be shooting for when you're doing these is you prefer 100% modulation. But the counter to that is we don't want to go too far, because if we get to this situation we call overmodulation down here in the lower left, the actual signal, when we're tracing it out, the envelope would look like this. And when we do that, we're causing this distortion in this area. Now, when it's actually being extracted on the other side by the receiver, this is the waveform that's going to be extracted, and that's a clear distortion in the signal, and that's going to make it hard for us to extract that information appropriately. So in order to do that, to avoid that, we want to make sure, so to avoid overmodulation, capital V sub M should always be less than or equal to V sub C. Okay? So, moving forward. So, one of the skills you're going to be asked to do along throughout this course is being able to find M from a plot. And one of the things that we already know is that M equals V sub M over V sub C times 100%, right? But in this case, we don't know what V sub m is, and we don't know what V sub c is either. We can find V min, and we can find V max, and we're going to have to use those to be able to find out what m is along the way. And we can also find V sub m and V sub c from V min and V max. And I'll show you those equations and how we're going to extract that information. So first, V max is going to be the maximum voltage that you can extract. So right about there. And our V min is going to be our minimum voltage. Right about there. And so we'll label those, and V min. And then our equations, and you're going to want to write these down on a note sheet somewhere so that you can use them. We'll have V sub m equals V max minus V min over 2, and V sub c equals V max plus V min over 2. And then we can use this again to find m, right? And if we use Vm over Vc times the 100%, this then becomes V max minus V min all over V max plus V min times our 100%. And that's just from substituting in the different values. So we say, hey, and doing some simplification, that comes from here, and that comes from there. So let's actually go ahead and take this to a practice problem, and we will apply it there. So if a carrier signal V sub c of t is 9 times sine 2 pi 5000 t volts is modulated by a sine wave of V sub m of t equals 7.5 sine 2 pi 440 times t volts, what's going to be the percentage modulation of the resulting AM signal? So go ahead and pause the video, look back at your equations, and go back and figure out what m is, and we will come back and work that. Okay, so now that you've returned, let's go ahead and look at what this is going to be. So we remember m equals V sub m over V sub c times the 100%. And we go ahead and say, okay, we know what V sub m and V sub c are from those two equations, so V sub m equals 7.5, because this comes from little V sub m of t, right? That's the source for that. And then capital V sub c equals 9, and that comes from lowercase v sub c of t. And then we just go ahead and set the equation up. 7.5 divided by 9 times 100% equals m. Bust out the calculator, and we end up with m equals 0.833 times 100% equals 83.3%. So, all right, at this point, I'm going to go ahead and stop this video, and we will pick it up again, and we're going to start addressing the AM amplitude modulation in the frequency domain. Okay, so picking it back up, we're talking about amplitude modulation in the frequency domain. So if we recall back to earlier slides, we remember this definition of our signal, of our amplitude modulated signal, and just give that a cursory review. We're going to carry that over to some new slides. And then if you remember, what we've talked about thus far is we have our time domain information signal, and then we have our carrier signal as well. And when that amplitude modulator spits it out, we have this amplitude modulated wave. And then if you think back to chapter 19, where we talked about the frequency domain, and we end up with a plot that would look like that for our information signal and like this for our carrier signal, the question becomes, hey, what does that amplitude modulated wave look like in the frequency domain? How do we put those together to get that information? So if you recall, when we are doing frequency domain information, we are going to get all our information by inspection. So we are actually going to look at the mathematical expression, so inspection of the mathematical representation of the signal. So of the signal. Okay, so this signal here doesn't give us a lot to work with. So we actually have to apply some trigonometric properties in order to figure some information out. So what we'll do is we'll go ahead and we'll translate that over here. So we have V AM of t equals V sub c plus V sub m of t times, and let's just go ahead and expand it now. V sub m cosine 2 pi f sub m of t, and all of that times cosine 2 pi f sub c of t. And for those of you who don't remember, I don't expect you to recall, or you can look up, and I suggest you do, so you can get some of these properties written down, that if you have cosine of A times cosine of B, you get 1/2 times the quantity of cosine A plus B plus cosine A minus B. Now, one of the things I want you to take into account here is that A will be greater than B in these situations, and the reason you can do that is because your multiplication is always commutative, meaning you can move those back and forth as necessary. It doesn't matter where they're located, they can be switched around. So let's go ahead and look at this signal a little bit closer, and we're going to break it down so we can get a more reasonable expression. So we have our V sub AM up there, and if we expand that out, we're going to end up with VC times cosine 2 pi f sub c of t plus V sub m cosine 2 pi f sub m of t times cosine 2 pi f sub c of t. We're just going to go ahead and apply that expression there using our trigonometric identity there, and then we'll end up with V sub c of cosine 2 pi f sub c of t plus 1/2 times the quantity V sub m cosine 2 pi f sub c f sub c plus f sub m times t, and then plus V sub m cosine 2 pi f sub c minus f sub m of t, close parentheses, close quantity. So with this, we can expand it out, and we'll end up with this really long expression, V sub AM of t equals V sub c cosine 2 pi f sub c times t plus v sub m over 2 times cosine 2 pi f sub c plus f sub m times t plus v sub m over 2 times cosine of 2 pi f sub c minus f sub m times time. Now, we should slow down here and look at some things. So the first thing I want you to look at is that this is our original carrier signal. Then, when we look at these other pieces, we're going to have two things in common. Our amplitude is going to be the same for each one of these separate signals. And in these separate signals, we have two different signals. We have the higher frequency signal, we have f sub c plus f sub m, and then we have the lower frequency, which is going to be f sub c minus f sub m. You can think about this formulaically. You're going to have your carrier component, and then you're going to have your higher frequency and your lower frequency component. Each one of them has the cosine, has the 2 pi, has time, but you're going to have to be aware of what the frequency component is. So frequency component of the carrier is always f sub c. The frequency component of your higher is always f sub c plus f sub m, and the frequency component of your lower frequency portion is going to always be f sub c minus f sub m. And then for those higher and lower frequency components, you're always going to have their amplitude, the original amplitude of that message, divided by 2. And we're going to talk some more about this later on, but right now we're going to move into how this is going to look as a frequency plot. So we have that signal. And what we're going to do is we're going to copy this, and we're going to bring it over to the other slide, paste it there, slide it into place. Okay, so now that we have this, I'm going to erase some stuff. Now, what we're going to do is we're going to build that frequency plot. And if you remember, when we're doing our frequency plot, the only things that we're concerned about are the frequency and the magnitude of the amplitude. And when I say magnitude, that implies that we're only going to take the absolute value of that. So at any point in time, you have an amplitude, let's say v sub I, then when we're looking at that frequency plot, it's always going to be the absolute value of v sub I, whatever that amplitude is. So here we have our magnitude, and here we have frequency, and this is going to be in hertz. And then what we're going to do is we're going to say, hey, we care about this and we care about that for this signal. So let's go ahead and plot it out, and we'll go ahead and say that this is f sub c and that our magnitude there is that. So that is, call that v sub c. Now let's go ahead and say that we know what v sub m is, and we can then do these as well. So let's say that the f sub c plus f sub m, that's going to be this here, f sub c plus f sub m is there. And now if our v sub m were right here, we need v sub m over 2. So this is where our v sub m over 2 is going to end up. Draw that across, and now we just make our spike right there. And then we're going to do a similar thing for our lower frequency, where we just bring it down to the left hand side, and we'll say that this is f sub c minus f sub m, and we just bring that spike up to that line again. And that's going to be how we build this. We're going to look for those key components of frequency and magnitude, and then we're just going to make sure that each frequency is plotted with its corresponding magnitude. So in this case, we have, maybe I should have used different colors. We have V sub c paired with F sub c. We have F sub c plus F sub m paired with V sub m over 2. And then we're going to have our V sub m over 2 paired with F sub c minus F sub m. And I'll just overwrite that real quick, just to keep things straight there on the slide. Okay, so we will take that and we will move forward and add some other information. So when we do this, when we modulate those frequencies, and we have those upper and lower portions like we see here, we're going to call those our lower sideband and upper sideband. And we can see here we've said, hey, this is our lower sideband. We're going to keep in orange, and then we'll go ahead and take our upper sideband, which we'll keep in purple. And then if we go ahead and recall our example, so recall the tuning fork example, where we had F sub m equaled 440 hertz, and we had F sub c equaled 5,000 hertz. Then if we were to try and make the frequency plot for that, we're going to end up with something that looks similar to this. And right here we're going to do frequency, but we're going to go ahead and put that in kilohertz. It's just going to be easier with that 5,000. We have our magnitude there on the vertical axis. Start at 0. And what we're going to do is we're going to go ahead and plot that corresponding portion for F sub c. If we remember that V sub c in this situation equaled 10 volts, and that our V sub m was equal to 7.5 volts. So we go ahead and work this out. We're pairing V sub c of 10 volts there with 5,000. So if we say that this is 5 kilohertz, that's 5,000 hertz. We can then bring that up, draw the spike right there, and that's going to be representative of our carrier frequency. Now we're going to draw in that lower sideband. That lower sideband we'll do in orange. We're minusing 440 hertz, and that's going to give us, and we're not going to keep this to scale, but we'll say that this is right here, that's a 4.56 kilohertz, and that's going to have a height, in this case, because we're taking V sub m over 2, is going to be 3.75. So we'll just say that's right there. Bring that down, and then we'll call that 3.75 volts. Let's go ahead and add in that upper sideband. We're going to say that that's located here, again, not to scale, 5.44 kilohertz, and put that spike in there. So that is going to be how we're going to plot those, how we're going to break those pieces down. If you have any questions on this, please let me know. But otherwise, I'm going to break the video and we're going to move over to the next portion where we're going to talk about bandwidth and then some more complicated signals as well. So when we previously talked about bandwidth, we talked about bandwidth being the difference between the highest transmitted frequency and the lowest transmitted frequency. And that concept is going to stay the same, but our equation is going to change slightly. Instead of bandwidth equaling f1 minus f2, in this case, bandwidth becomes fc plus fc plus f sub c plus f sub m. This is our highest frequency, minus our lowest frequency, which is f sub c minus f sub m. And when we do this, and we do some cancellation, sorry about that, we're going to get this canceling with this, and then we end up switching this sign, and we end up with the bandwidth equals 2 times f sub m. Now, in this case, this can be tricky, because if we have multiple frequencies, which we're going to start talking about here in the next slide, this f sub m has to represent the highest frequency. The highest frequency in the message signal. Okay, be careful to note that, and that you're so you don't make any mistakes in the future, because it can be easy to mix up. So one of the other things to note is that this requires, this is twice the bandwidth. And if you remember one of the last slides in chapter 19, we talked about how expensive bandwidth can be. So this is actually a delicate balancing act where we want to try and minimize the amount of bandwidth we're using, because we know it's expensive, but it may be required in order to make sure all the information can be transmitted appropriately. So be aware of that. Nothing crazy outside of that. All right, so a slightly more complicated signal. So we have an information signal that's made up of 2 sine waves. In this case, it looks like this. So this is what our information signal looks like. V1, or V sub 1 times cosine of 2 pi f sub 1 times time, plus V sub 2 cosine 2 pi f sub 2 times time. And what I've done is I've already gone through and raced through the math, so you guys don't have to sit through that, but let's point some things out as we move through it. When we're finding out what the amplitude modulated wave looks like, we have V sub m here. And what we do is we then turn around and substitute that in right there. Then you will see, if you look through it, that we take this carrier wave frequency and we distribute it throughout. And it gets put in there, and then we end up calculating using that trigonometric property, and we end up taking this chunk here and turning it into this chunk there, and this chunk becomes that chunk. So all of these are going to be used to pull the information out, so we can do things like build our frequency domain representation, as well as find our upper and lower sidebands, as well as our maximum and minimum frequencies, so that we can determine our bandwidth and go from there. So let's go ahead and look at this practice problem, which is going to kind of try to apply a bunch of those different skills. So the first thing we're given is we have a 2-chime doorbell, and it has these frequencies right there, 440 hertz and 349 hertz. And we're using a very low frequency communication band to transmit that, and it's a FC of 20 kilohertz. And the chimes themselves, so V sub m, have a 10 volt amplitude, and the carrier's amplitude is 20 volts. So we're going to then use that information to sketch a frequency domain representation and determine the bandwidth. So the first thing I want you to do is go ahead and pause the video, use what you know to try and work through this problem. And when you're done with that, if you're stuck, or when you're finished and you want to come back and check it, come back here and I'll work through it. So if we look at this representation, one of the things we can do is we can actually write the entire signal out if we wanted to, but we don't need to. But what I'm going to do is I'm going to say, hey, I know what V sub C is. It is 20 volts. I know what F sub C is. It is 20 kilohertz. I know what V sub M is. It is 10 volts. And I know what F1 is. It's 349 hertz. And I know what F sub 2 is. It is 440 hertz. So if I'm trying to figure out the frequency domain, all I need to know is the frequency and the amplitudes. But if we remember, we're going to end up with our frequency domain plot. And the first thing I started off by plotting was the carrier frequency. So when I do this, I'm going to say frequency, and I'm going to say I want this in kilohertz because I have that 20 there, and I need to figure out first where that frequency, carrier frequency is. Let's just put it right there. So that's 20, and we're going to go ahead and give this a height of 20 there, and we'll just go ahead and plot that like so. Now I need to figure out those sidebands. To figure out those sidebands, I'm going to say I have an upper and lower for 349 and an upper and a lower for 440. So let's figure out what those are. If you remember, by looking back at your equations, you're going to have f sub c plus f sub 1, and then you're going to have f sub c minus f sub 1, and then you're going to have f sub c plus f sub 2, and f sub c minus f sub 2. And those are each going to give us different bits of information, and we'll calculate those and put those on here so we can plot those appropriately. So if we do this, we figure out that this is going to be f sub c plus f sub 1 will be 20.349 kilohertz. And then here, this is going to be 19.651 kilohertz. Over here, 20.44 kilohertz and 19.56 kilohertz. And we can go ahead and start plotting those. So let's go ahead and plot our f sub 1. We'll plot those in orange, and we're going to end up with, we're not going to try and keep this to scale, but we will keep it in order. So this will be our 20.349, and we'll have this over here. And we know these are all going to be the same height. We'll figure out what the magnitude of that's going to be in a second. We're going to call this 19.651. So then we're going to go ahead and plot the f sub 2 components in green, and again they're going to be the same height, and we're going to say that that is 20.44 kilohertz, and we have one over here, and that is 19.56 kilohertz. Now when we're looking at this, we remember these are all Vm over 2 in magnitude, and that's going to be 10 over 2, just 5. And they're all going to be that same amplitude because they all have the same original amplitude. So that has a magnitude of 5. And this is going to be our frequency plot of this signal. So let's move on to calculating the frequency, bandwidth, sorry, of this overall signal. And if you remember, we came up with the equation from before where bandwidth equals 2 times f sub m. And f sub m in this case must be the maximum frequency inside of our message signal. So in this case, it actually becomes 2 times f sub 2, which is going to be 2 times 440. That equals, and that's hertz, 880 hertz. Now the other way that we can do this is we can just take that maximum frequency, so equals f max minus f min. And if you remember, we can do that because ultimately we're trying to use that highest frequency and the lowest frequency that's in our signal. Just come back over here, f max minus f min, and that becomes 20.44 kilohertz minus 19.56 kilohertz. And if you do that math out, you're going to get 0.88 kilohertz, and that equals 880 hertz. So that checks out both ways with the same answer. The only difference is that you need to be very careful using this one so that you make sure you're using the maximum frequency in the message Okay, so be careful with that. I would default to using this, though it might get a little tricky when you have to do some unit conversions. Moving on to this next question. Let's look at this signal, and we can see that we are given a carrier signal with an amplitude of 20, frequency of 5,000, and we have a message that has an amplitude of, or two components, one with an amplitude of 4 and a frequency of 200, and a second with a amplitude of negative 6, but we're just going to see that as a magnitude of 6, a frequency of 400, and this one actually has a phase component of 4 pi over 11. And again, it wants us to sketch the frequency plot and calculate the bandwidth. So we'll use the same methods we did before, and we're going to start by writing down our V sub C, our F sub C, our V sub M, and in this case we're actually going to have two V sub M's, so we'll have a V sub M1 and a V sub M2, and then we're going to go ahead and write down the corresponding frequencies as well, F sub 1 and F sub 2. So we will keep these matched up by color. So V sub C, 20 volts, and the frequency there, 5,000. So for F sub 1 and V sub M, or sub 1, we're going to have 4, and F sub 1 will be 200, and then we will have V sub M2 as negative 6, and then we have 400. So in this course, we are not concerned with phase for our frequency plots, so we're going to ignore that at this point in time. So when we're doing this, now we have all the relevant pieces. We need to go ahead and start building that plot. So draw it out. Magnitude here is going to be in volts, and we'll have frequency. Again, because we have that 5,000, we're just going to go ahead and put it in kilohertz. Just makes it a little bit easier to work with. And then we're just going to go ahead and put that carrier frequency right on there. And we'll just 5 right there. Let's go ahead and say that this is 20. Just plop that right in there. Now, when we're looking at our first component, we know that we have, again, our F sub C plus F sub 1 component and the F sub C minus F sub 1 component. And in this situation, we need to go ahead and calculate the actual amplitude before we do anything else, so that we can make sure that we plot it with the right height. So when we do that, let's go ahead and calculate that. So we have, in this case, V sub M over 2, but this is V sub M sub 1, so that'll be 4 over 2 just equals 2. So we're just going to go ahead and plot a 2 on there, and we'll go ahead and we'll say, hey, what's our F sub C plus F sub 1? That's going to be 5.2, and then we'll have 4.8 as our F sub C minus F sub 1, and those just have heights of 2. Then we need to do this same process for our second component, and we have F sub C plus F sub 2, and that's going to be 5.4, and F sub C minus F sub 2, and that'll be 4.6, and then we have our V sub M 2 over 2, and that equals negative 6 over 2. But remember, when we're plotting these, we're only doing the magnitude, so we'll take the absolute value of that, and that becomes 3. So we'll just have a 3 right there, and then we'll find F sub 5.4 of, and that'll be called right there, and then we'll have 4.6, and we'll call that, I should label it 5.4, 4.6, and we've got it all plotted out. So now that we have that plotted out, we should be able to calculate what our bandwidth is going to be. Let me move this out of the way. There we are. So now that we're calculating that bandwidth, we're going to go ahead and say, hey, our bandwidth is 2 times f sub m, but we got to remember this is our maximum from Vm, and in that case that's going to become bandwidth equals 2 times 400, because this was our maximum frequency, gives us 800 hertz. Or we can go again back to our straightforward, hard to make mistakes method, which is Fmax minus Fmin, which equals 5.4 kilohertz minus 4.6 kilohertz. Do some math, and you end up with 0.8 kilohertz, which equals 800 hertz. So if you're confused or lost, please go back, review that again, and then if you have any other questions or desire some further clarification, please let me know via email, via the forums, via the live interactive EI sessions. One way or another, we'll try and make sure that you have the information so you can be successful in working these types of problems. So the last thing we're going to talk about is demodulation. So demodulation is essentially undoing modulation. And if you recall, when we talked about things, you had that envelope of our signal. And when we had that signal was trapped inside here. And what's going to happen is there's hardware on the other side that is going to make it so it only looks at the positive portion, and it's going to connect the dots between the pieces that it gets so that it can start putting together this piece. You are not responsible for knowing anything other than the fact that demodulation undoes modulation. So I don't want you to spend a lot of time on it, but understand that when we did this in the frequency domain, because this is time, seconds, and over here, if we're looking at this in the frequency domain, we took a signal that was down here, in the lower end of the frequency spectrum, and we moved it. We shifted it all the way out here, and when we did that, we ended up with our carrier spike and some sideband spikes. To demodulate, all it's going to happen is it's going to shift it back down. So now to demodulate, it goes back down this way. And we use some filters to clean some things up, pull some stuff out of there. So what I can do is I will show you that. Shifts it down, and then filters it, and it gets that information cleaned up. So all we're left with is something that looks exactly like our original signal. So this is horrible demodulation, and this is the modulation. What's hidden in all this is all of the filters. Not that you need to know about it, but there's lots of filtering happening in order to make sure clean information is making it from one component to the next component along the way, and that noise is being filtered out of it. So understand demodulation undoes modulation, and it's based on this shifting. So modulation, we're shifting up; demodulation, we're shifting down. And again, if you have any questions, concerns, let me know, and I'll do my best to get back to you. Have a good day.